thing you need to know about limits is how to write them properly. So let's talk about notation. I use cursive when I do my limits, but I don't care if you print, but I usually just do this. Okay, a little bit kind of half cursive, half printing. Okay, so that is the abbreviation for limit. The correct notation is after the limit, what you're doing goes in parentheses. And under the limit goes the value that your variable is approaching, some kind of numerical value. We live in a world of limits. There's limits all around. You know, the limits that we would place on a toddler, for example, might be different than the limits that you have on a teenager in terms of like your own safety, speed limits. But mankind, humankind, we are born with the tendency to push the limits, okay, no matter what. If you tell a little toddler, hey, you can't go into the street, okay, well, it's a limit. You tell them because why? Because you want them to be safe, right? But what will a toddler do? Okay, well, how close can I get to the street? Who can I put my foot in? What if my ball goes into the street? What if, you know, and then they just want to push the limit, right? And if you have a curfew, it's a limit, okay, usually set on you either by a law, you know, if you're within the first 12 months of your driver's license and you got to be off the roads by 11, okay, and then as you have your license longer, that it goes out longer, but we push the limits. What's the how late, you push it when you come to school. I bet all of you know what the last time is at your house that you can leave and still get to school without being tardy. You probably know exactly what that minute is. Well, you're pushing the limits of that. Okay, so we live in a world of limits. Mathematically, we notate them this way. Okay, as long as you have variables in your work, the limit notation should be there. And so if I, on a test or a quiz, on a homework, I won't mark you off, but on a test or a quiz, if I note in your work that you're still working with variables, but you've dropped the limit notation, then I will deduct a little half a point or something from that, because that's just incorrect notation. It would be like, you know, you turning a paper into Mrs. Winters and then deciding to just leave off all the punctuation and hoping that she could figure out what you meant. All right, that's kind of the same thing. Or if you're writing something that you're turning in for a test or quiz, it probably should be proofread for the right notation. Yeah?
When you're working several times, say with f of x, trying to get a variable in a certain place to do something, do you have to write limit x, arrow a, every single step you take?
Every step you take, yeah, okay. That's the correct way to do it, yeah. Prefaced by an equal sign every time you make a step change. Okay? All right. So that's the notation. I'll demonstrate how to do that the right way. There are 3 ways that we're going to talk about of how to evaluate a limit. In math, a limit is you aren't guaranteed to ever get there. You could get really close to it, but you might not ever get fully there. So evaluating a limit in 3 ways. All right, the 3 ways we're going to talk about today. 1. You could evaluate a limit by evaluating a graph. So that's the graphical approach to a limit. Those are going to be open and closed circles. How close can you get to that point? Number 2, direct substitution. That's where you can replace a variable with a number and come up with a numerical answer. And the 3rd way is the most common, which we will use. Algebraic simplification. That's why I had you practicing a little bit of factoring, because you're going to need to know some factoring, some algebra, maybe some conjugates, on how to simplify something using algebraic techniques to evaluate the limit that way. All right, so you've got your limits, notation, and then you have the approaches that we'll use, and then I'm just going to demonstrate several of these. Okay, could you have your graphing calculators out for me? Because our first one is going to be graphing examples. Okay, example A, under a graphing example. You may be asked to evaluate the limit in parentheses of x cubed minus 5 over x minus 2, and to evaluate that as x approaches 2. Now, what's the problem with the number 2 right now? Okay, it makes it 0. Let's try different pronouns. Okay, the number 2 would make what 0? The denominator 0. Okay, if we tried to plug 2 in, we would be violating one of those cardinal rules of math that says you shall not divide by 0. 2 is not in the domain. But this does have a limit. So what if we're not actually plugging in 2? What if we're getting really close to the number 2, like 1.99999999999? Okay, would that be allowed? Could we plug that in? So let's take a look at the function and see if we can determine what the limit is just visually. Okay, so go ahead and graph that. Make sure when you do use your graphing calculator that the numerator and denominator are each in parentheses, because otherwise you will get an incorrect graph if you haven't put both of those things separately. All right. How you would do that. Okay, you would say the limit as x approaches 2 minus. That little minus does not mean a negative number. It means you're on the left side of 2, like 1.9999999 repeating. And so it appears visually from the graph that we're tanking out on the side of 2, and that limit then is negative infinity because I'm heading down in a negative direction. That's the asymptote. It also appears that on the right side, so you write 2 with a little plus, which means you're just a tiny bit more than 2, like 2.000000001, and the limit of that on the right side of the graph has a positive infinite asymptote, and so you would specify that that's positive infinity. So there are different limits on the left side and the right side. Okay, let's explore the limit of the function x cubed minus 1 over x minus 1. And let's do that approaching 1, because 1's not in the domain, but let's find out what's going on visually with this function. All right, so I'm going to pause the recording. So we know that there's something going on at 0, and so we would say, okay, well, what is going on when I approach 1 from the left? And according to the table, as I was exploring with my calculator, it looked like it was 3 minus. Okay, remember, that doesn't mean negative 3. That means it was something tiny bit smaller than 3. It was 2.997. If I went to a smaller decimal than that, I think that this can handle, let me see, can I make it go to the 10,000? Oh, better that one. Yep, okay there. Now I'm even smaller. Oh, you can't see. Okay, yeah, so it's like, it's 2.99999, so it's something barely smaller than 3. And then on the right-hand side of the limit, I'm at something a tiny bit larger than 3. But at 1 itself, there is a hole. I can't get to 3. There's no way to get to 3. I'm either a little bit short or I'm a little bit over, but I can't ever get to 3 itself. I'll never be able to achieve that limit. I just approach the limit. So that's sort of a graphical explanation. Jason, question? No. Okay. So you're going to have to be smarter than what you see on a calculator, especially with the domain. If you know the domain has a problem at 1, don't get suckered into thinking it's a smooth graph. There's something missing. Okay, the second one, direct substitution. Direct substitution is when there is no problem plugging in the number at all. It doesn't violate the domain. You can just drop that number in. So this is example C. Say the limit as x approaches 3 within the function x plus 4. Well, that function has a domain of all real numbers, so it doesn't matter. I can drop the number 3 directly in. Notice when I drop number 3 directly in, I don't need limit anymore because I don't have any variables anymore. I've exchanged the variable for a number, and I can evaluate it to be 7. So these are the easy ones. You'll have very few of these in your homework. We wish there were more. All right. Okay, x approaching -1. 2x squared. Okay, again, domain for that's all real numbers, so I can drop that number in no problem. I'm going to get 2 times the quantity -1 squared, which will give me +2. Okay, so notice that as I exchange a variable for a number, then I don't need the limit notation anymore. Okay, example E. The limit as x approaches pi of the bracket function of x. Okay, the bracket function of x has a specific job like the absolute value. We call it a step function or an integer function. Okay, it takes the integer smaller than the number that you're plugging in. Okay, the integer, it's called the integer function, and it always takes the integer function smaller than the number you're plugging in. So when I exchange the variable for a number, the result is going to be the number 3 because it is the integer smaller than it. So you got to really watch that, especially when you're dealing with negative numbers. So for example, if you're plugging in the number -1.5 into the integer function, okay, exchange the variable for the number -1.5, the value on that is the integer lower than that, which is what? -2. Okay, it's got to be the integer smaller than the one that you're plugging in. Okay, that's called the integer function. So any questions about direct substitution? Okay, then that leads us to algebraic simplification. This is where you don't have the access to a graph. And all you have is what you know about algebra. So I'm going to go back. And our example G is actually going to be the same as our second example. We do the limit as x approached 1 of x cubed minus 1 over x minus 1. So if you did not have access to a graph or a table or anything like that, okay, then you're going to need to do some algebra on that, which is usually some kind of factoring. Now, I am keeping the limit notation going because I'm not yet exchanging a number for a variable for a number. So I'd factor that. That's the difference of cubes. Okay, it factors well. The difference of cubes factors into x minus 1 and x squared plus x plus 1. You can Google the difference of cubes if you don't remember how to factor. And then over x minus 1 still. So that leads us to something that we can reduce. Because as we factor out the numerator and the denominator, I still keep my limit notation going because I have not yet exchanged a variable for a number. Now I can exchange the variable for a number, so I'm going to get 1 squared plus 1 plus 1, which is 3. So this tells me, algebraically, which I already knew from the graph, that the limit is approaching 3. Now it's never going to get to 3. It'll get as close as 3 minus or 3 plus, but it will never actually get to the number 3 because of the hole in the original domain. But you can prove it algebraically. Okay. All right, let's try the limit of the function 2x minus 4 over x cubed minus 2x squared. All right, that is good. Andrew says, what does x go to? Well, it's going to go to a problem number. Okay, what are the problem numbers for this particular function? What would be no bueno? 0 would be no good, because if I plug 0 in, I would get 0 in the denominator. What else would be no good? 2 would also be no good. Okay, so the limits are always going to approach one of those numbers that are no good. All right, let's see what we can do. Let's do 2. Both of these are factorable again. So the limit as x approaches 2. And we'll factor the numerator into 2 times x minus 2. We'll factor the denominator into x squared times x minus 2. We'll show that the factors of x minus 2 reduce. We'll show that what we're left with is 2 over x squared. And then when we exchange the variable for the numeral, for the number, 2 over 2 squared, which would be 1/2. So we'll know that this function approaches 1/2. It will never get to 1/2. It'll get to the left of the 1/2 and to the right of 1/2, but it will never actually get there. Now suppose in that same problem, just go side by side to that, suppose you had the exact same problem and you were doing 0. So same question to the other point of where the domain does not exist. You still use the factoring technique, so I'm just going to jump to 2 over x squared. Okay, can I plug in 0 this time? I still can't. Last time I could plug in the number 2 because the 2 factor factored away, but I still have a problem here. So then you're going to have to separate this into, okay, I can't plug in 0, but I could plug in 0 minus, and I can't plug in 0, but I can plug in 0 plus. Do you see how limits allow a mathematician to sort of like get around the rules? Well, I'm not plugging in 0, I'm plugging in 0 minus. That's legal, okay? You just said I couldn't plug in 0. You didn't say I couldn't plug in 0 minus, or you didn't say I couldn't plug in 0 plus. It's like the kid in the back seat who says, I'm not touching my brother, right? And he's holding his finger, like, right? I'm not touching him, I'm not touching him, I'm not touching him. Okay, but it's just really irritating. Okay, so this is a mathematician's way of sort of like, well, I'm not plugging in 0. Watch me. Okay, so let's try that. What happens if we plug in 0 minus and we square it? And what happens if we plug in 0 plus and we square it? Okay, we're not plugging in 0. We're plugging in something negative. What happens when you square something negative? What do you, anything negative, right? You get a positive number. And so by squaring this, I now get a positive number. And 2 divided by the smallest positive number you can think of, but it's not 0. It's the smallest positive number possible without being 0. What will that produce? It'll produce infinity. When you divide by something small, it produces something very, very large. Okay, and so this will produce positive infinity. The bottom one is not very interesting because it stays positive and also produces positive infinity. And so that limit was positive infinity on the left side and the right side, which means the sides of the graph are doing what? They're both shooting straight up, right at that number.